Alright, so for oxygen nucleophiles, in the presence of water, an aldehyde or a ketone is in equilibrium with what's called the hydrate. So you can see the hydrate has two hydroxyls on the same carbon, so we call that geminal. You know, when you have two groups on the same carbon, that's geminal. So geminal hydroxyl, we call that a hydrate. So the equilibrium generally does not favor the formation of the hydrate, except for really simple aldehydes like formaldehyde. The reaction is very slow unless it's done under acidic or basic conditions. So let's take a look at what happens when we do the same reaction in basic conditions. So if I have a strong nucleophile like hydroxide, a base, it can attack the carbonyl carbon. I make this oxide and then I do a proton transfer to produce my hydrate. So there's the hydrate. Alright, what if I do the same reaction in acid? You can probably guess the first step is going to be protonation of the carbonyl to render it more electrophilic and more reactive towards a weak nucleophile like water. And then I produce an oxonium, I undergo a proton transfer, and I end up with a hydrate once again. So of course, in acidic conditions, I have to activate the carbonyl with acid before I can do the nucleophilic attack with my weak nucleophile. So these are just a couple of points that come up in the book. I'm going to summarize this really quickly. You see the two stars that I have here. A strong base can't exist in an acidic environment. So if you're practicing your mechanisms in this chapter, and if you're doing, say you're forming an acetal in acid, and we'll talk about acetals in a second. If you're doing it in acid and you start drawing hydroxide, you're doing something wrong. Same thing. It says if we're doing it in a basic environment, if we're doing these mechanisms in a basic environment and you start drawing hydronium, well, there's a problem there too. So just keep an eye out for those kinds of things. So it says alcohols can attack a ketone or an aldehyde, and we produce a brand new functional group called an acetal that I have in this blue box here. I also want to point out that these square brackets around the hydrogen ion, the proton, those mean that it's a catalytic amount of acid. So I know that from general chemistry you're probably used to that representing, concentration, but here it means a catalysis or a catalytic amount of hydrogen. So under acidic conditions, one ketone or aldehyde reacts with two alcohols to form an acetal. So stoichiometry doesn't come up a lot in our class. It does come up from time to time, but if you notice that the ratio here is 1 to 2, so we need 2 alcohols for every ketone. And what else? The commonly used acids for this acetal formation are para-toluene sulfonic acid and sulfuric acid. H2SO4, everybody's familiar with that. But para-toluene sulfonic acid, the acronym for that is PTSA. Alright, so this is mechanism 19.5. I recommend practicing this mechanism and being able to draw this mechanism. Now this is showing the formation of an acetal. So you see that there's an acetal down here at the bottom, forming an acetal from a ketone under acidic conditions. So of course the first step is going to be protonation with an acid, and then you can see that I have number 1 here by the first equivalent of alcohol that acts as a nucleophile. So then after a proton transfer, another proton transfer, and a loss of water, we get a new electrophile. So now we have another electrophile, and now alcohol number 2 can come in and do a nucleophilic attack. We produce another oxonium. We do a deprotonation, and we end up with our acetal. So I would recommend practicing this mechanism and being able to recognize all the steps. Also, I want to point out that when you have one ether, and one alcohol on the molecule, we call that a hemiacetal. So first you obtain a hemiacetal, and then you proceed through that to the acetal. So acetal formation is an equilibrating process. For simple aldehydes, the acetal is actually favored at equilibrium, but for ketones, the acetal is not favored. So you can see that I have some notes written down here already. So if I erase what's here on these equilibrium arrows here, you can see that they've shown that the equilibrium actually lies to the starting material, to the ketone in this case. So the question is, how do you drive the reaction forward? And the way you do that is by removing water. So that's based on Le Chatelier's principle. If I can remove water, it's going to push the reaction to the right in order to restore equilibrium. And the tool that you use to do that is a piece of glassware called a Dean-Stark apparatus. So if you want to Google that and look at the Dean-Stark apparatus, I would never ask you anything about it. But it's kind of interesting to see interesting ways that scientists have devised to get molecules to do what they want them to do. Anyhow, also, if you use a diol like ethylene glycol that's shown here in red, we get a cyclic acetal. So you can see it proceeds through the hemiacetal, and then you do another 4 steps to get the cyclic acetal. So cyclic acetals can actually be used as a type of protectant group, and I'll do more on that later. But I would recommend practicing mechanism 19.5 and being confident in being able to draw that mechanism.